Hi, welcome to Mathematics of Chemistry Review Part 1. My name is Dr. English, and today we're going to look at the basics of doing math of chemistry, also known as stoichiometry. Specifically, we're going to focus on a very brief review of significant figures, how to find the mass of a compound, determining percent composition, and finally working with hydrates. So let's first start talking about adding and subtracting significant figures, and as a result of looking at this, also talk about how to determine the number of significant figures in numbers. The first thing that you really need to know when you're adding and subtracting significant figures is that you've got to look at the numbers that you're going to have, and really you want to line up your decimal points. That is really key. Adding and subtracting is all about decimal point location. Now, the key thing to remember with adding and subtracting significant figures is your answer can only be as accurate as the least accurate answer. This is all about decimal point location and how many numbers you have following the decimal point. So let's look at the first example here. I have 8.11 plus 2.476. If I add these together on my calculator, I'm going to get 10.586. Now, the key thing to know here is that when I look at 8.11, it goes out 2 decimal places. 4.276 goes out 3 decimal places. This is my less accurate number. Therefore, when I line these up, I can only go out 2 decimal places, which means I'd have to take this 6 right here when I add them up and basically round up that 6. So the final answer when you're adding these two numbers together will be 10.59, going out 2 decimal places. Let's look at this other one. Now this is subtracting. When you subtract, especially looking at this first number here, which is 40.3, and we're subtracting 1.6954. Now the 1.6954 has a lot more decimal places after it than our initial number. There are assumed zeros here, 0, 0, and 0. But when we talk about the accuracy of this first number, we can only take it out to the first decimal place. If I enter this into my calculator and I subtract these two numbers, I'm going to get this big long number right here. But again, when I look at this, after I subtract these together, I can only go out 1 decimal place. Looking at this final answer that I get right here, this is what I'm going to have. When I look at this calculated answer right here from my calculator, and I basically round it in terms of significant figures, I can only go out 1 decimal place because my least accurate number only goes out 1 decimal place. Adding and subtracting significant figures, all about the decimal place location. Now let's look at some examples down here of just looking at numbers and determining how many significant figures are in each number. So I have 4,012. This 0 is considered significant because it's surrounded by non-zero numbers. The number of significant figures here is 4. 640. No decimal point at the end. The only 2 significant numbers are the 6 and the 4. So this would have 2 significant figures. 640 with the decimal place. Now this is significant. So 3 decimal places. If I look at the next number, 0.06030. One method that people use when looking at a number and saying, well, how many significant figures do I have, is called the Atlantic-Pacific rule. And if a decimal is present, you start over on the Pacific side of the United States, so a decimal is present, go across until you hit your first non-zero number, which is 6. So that 6 and everything that follows it as you go from left to right would be considered significant. So that would be 4 significant figures here. Again, in this one, 0.00254, decimal is present, so we're going to start over on the left-hand side, the Pacific side. You go across until you hit your first non-zero number, which is 2. And that and everything after it would also be considered significant, so that would have 3 significant figures right there. If you need more help with learning how to figure out how many significant figures a number has, go and look up the Atlantic-Pacific rule. My students have found that quite useful in the past. Now let's talk about multiplying and dividing significant figures, and to me this is the easier one to do. So the first thing that you're going to do is you're going to count the number of significant figures in each of the given numbers. Then you're going to multiply or divide the numbers as directed. the key point here, just like we had a key point with the decimal places with adding and subtracting, the answer should not contain more significant figures that are present in the number having the fewest significant figures. If I look at these numbers right here in this multiplication, I have 4 significant figures here, 2 significant figures here, and 5 significant figures here. If I multiply these together, I get this number. Now, this is just what comes up into my calculator, and this is truncated slightly. When I look at how many numbers my answer should have in terms of significant figures, my answer should have no more than 2 significant figures, because again, the answer should not contain more significant figures than are present in the number having the fewest significant figures. The 2.6 has the lowest number of significant figures, with 2 significant figures being present. Therefore, when I look at this, I'd say, all right, the 9 is the largest number here, being 90, so that's going to be significant. The 5 would be next, and then finally I'm going to round up the 6. So my final answer here would be 96. Now let's look at this one. 130 divided by 9.4. This has 2 significant figures because no decimal is present. This has 2 significant figures, therefore my answer should have 2 significant figures. When I put this into a calculator, I get 13.82978. My answer will only have 2 significant figures, therefore my answer will be 14. Always good to actually do the computation first and then round at the end. In my world, when in doubt, round to 3 significant figures. Now let's talk about how to find the mass of a compound, and this is a really important skill for this course. So let's talk about the gram formula mass. And the gram formula mass is defined as the sum of the atomic masses of all atoms present in a compound that represents 1 mole. And we'll talk about moles a little bit in the next review. The unit of measurement to use with gram formula mass is grams, or represented by a lowercase g. Now, this is representing 1 mole of something. If you had to find the mass of one atom, so a single atom, we would use the symbol of U. The symbol of U, which is on the front of your reference table. Now you might have seen in different textbooks the use of AMU for the atomic mass unit, but in New York State we use the symbol of U, so FYI. Gram formula mass can be used to refer to the masses of compounds that contain ionic bonds, covalent bonds, or both ionic and covalent. Now there's a bunch of different names that basically mean the same concept as gram formula mass. Sometimes you'll see it listed as formula mass, molar mass, the mass of 1 mole, or a more specific type of gram formula mass is molecular mass. But molecular mass only applies to molecules. So if they say find the molecular mass of this, or which of the following 4 compounds could you find the molecular mass, you'd be looking for the one that is an actual molecule, and if you know that it is a molecule, it is going to have non-metals only, because a non-metal it's covalently bonded, so therefore we could find the molecular mass of that. If I gave you sodium chloride, technically we wouldn't find the molecular mass of sodium chloride because sodium chloride contains a metal and a nonmetal and is an ionic compound. So molecular mass only for molecules. So let's look at some different examples of how to find the molecular mass of a compound. The first one we can look at is magnesium sulfate. The way that I approach this is I write out my element symbols. So this compound contains magnesium, sulfur, and oxygen. And then I ask myself, well, how many of each of these do I have? There's an assumed 1 here, and a 4 over here. For magnesium, that's going to be 1, sulfur is going to be 1, and oxygen is going to be 4. The atomic mass of magnesium is 24, so 1 times 24 gives me 24. Sulfur is 32, and oxygen is 16. And 4 times 16 is 64. So if I add these all up, I get 120 grams per mole. So let's look at C4H7OH. So I'm going to list this as carbon, hydrogen, oxygen, and hydrogen. And I know I'm repeating the hydrogen twice, but I'm going to keep things in order. If I do this, I have 4 carbons. Carbon has a mass of 12. I have 7 hydrogens, so 7 times 1, 7. I have 1 oxygen, and oxygen is 16. 1 times 16 is 16. And finally, there's an assumed subscript of 1 right there, so 1 times 1 is equal to 1, and 4 times 12 is 48. So again, I'm going to add these up, and my mass for this one will be 72 grams per mole. All right, let's look at the next one, calcium hydroxide. So again, I'm going to list my elements, Ca, O, and H. And here I have to be careful because I'm working with parentheses, so I'm going to have to distribute. So I have 1 Ca, 2 oxygens because the 2 distributes through, 2 hydrogens. So the atomic mass of calcium is 40. And then we have 16, and that gives me 32. And this is 1, and so this is 2. And I add all these up, and I get 74 grams per mole. Because these are all molar masses, so the mass of 1 mole. So this literally means 74 grams over 1 mole of the substance. The last one that I'm going to do is a little bit more complicated. We have ammonium carbonate here. So again, I'm going to list my elements. Nitrogen, hydrogen, carbon, and oxygen. Now, do you have to do it this way? No, you don't, but I make silly mistakes all the time. So this is my way of doing some type of like housekeeping to make sure that everything's on track. Nitrogen, how many nitrogen do I have? Well, I have an assumed 1 right here, so this is 2. 4 times 2 gives me 8. There's an assumed 1 by the carbon, so that's 1. And then finally 3 oxygens, so that's a 3. And then the atomic mass of nitrogen is 14, so that gives me 28. Hydrogen is 1, so that's 8. Carbon is 12. It's 12. And 3 times 16, that's 48, for a grand total of 96 grams per 1 mole. So that's finding the gram formula mass, the molar mass, the formula mass, the molecular mass for this one right here, this alcohol, just in general how to find the mass of a compound. Let's talk about determining percent composition. Percent composition represents the composition as a percentage of each element compared with the total mass of the compound. Usually if you get a question like this on the Regents exam, they're going to ask for the percent composition of one particular element or water, and we'll talk about hydrates in a minute. The formula for percent composition is found on table T, so it is nothing that you need to memorize. So the percent composition formula is the percent composition of mass, mass of the part, that's what you're specifically looking for, mass of the whole compound times 100. Let's look at an example here. This example asks to find the percent of mass of nitrogen in aluminum nitrate. The first thing that you should do is find the gram formula mass of aluminum nitrate. So aluminum nitrate is AlNO3, 3. Just like I did before, I'm going to say to myself Al, N, and O. So how many aluminum do we have here? 1. How many nitrogens? Well, the 3 is going to distribute, so that's going to be 3. How many oxygens? Well, 3 times 3 gives me 9. Then I'm going to go to my periodic table. I'm going to look up the atomic masses of these, and I see that aluminum is 27, so that gives me 27. Nitrogen is 14, so 14 times 3 is 42. And 9 times 16, if we multiply that out, is 144. If I add these up, I get 213. And for all of the calculations that I'm doing today, just for the sake of time, I am rounding them to the nearest whole number. If your teacher is adamant about using the decimal places that are listed on your periodic table, by all means, please do so. This right here represents my total mass of the compound, so the mass of the whole. To set this up, what I'm going to do is I'm going to take the part, which is the nitrogen, and I want the entire mass of the nitrogen. So the whole 42 is going to be the 42 on the top. That's the part. The whole is the mass of the entire compound, which we just figured out was 213, and we're going to multiply that times 100. 42 divided by 213 times 100 gives me 19.7%. No specific reference is made here to number of significant figures. So in these situations, what I do, if they don't say, please give your answer to a certain number of significant figures, I go to 3 significant figures. That's typically my rule of thumb. Let's look at 2 more examples. The next one asks to find the percent by mass of potassium in K2CrO4. We have K2CrO4. I'm going to list my elements again, K, Cr, and O. I'm going to look at how many I have of each. So I have 2 potassium, 1 chromium, 4 oxygens. Potassium is 39, and 39 times 2 is 78. Chromium is 52, and oxygen is 16. 4 times 16 is 64, and if I add these all up, I get 194. So 194 grams. Again, when we do this, it's going to be part over the whole times 100, and it is always in your best interest to write out the formula before you put the numbers in. Write out the formula, please. It'll make your life a million times easier. The part here is the potassium. The 78 is going to go on the top. The whole is the 194, so that's going to go on the bottom, times 100. 78 divided by 194 times 100 is 40.2%. So 40.2%. Let's look at the last one. A compound is formed when 9.03 grams of magnesium reacts with 3.48 grams of nitrogen. What is the percent composition of each element in this compound? So what do I have here? Well, I have a mass of magnesium. Magnesium is going to equal 9.03 grams, and I have a mass of nitrogen, which is 3.48 grams, and I don't have to do anything with these except add them together to get the total mass. This is a different type of setup with this problem. 9.03, 3.48, if I add those together, I get 12.51 grams. This is going to be my total. The next thing I have to do is find the percent composition of each element. So to find the percent of the magnesium, again, it's going to be part over the whole times 100. Well, the part is the magnesium. So this is going to be 9.03 grams over the total, which we just added up, so that's 12.51 grams times 100. And if I work that out, I get 72.18, and I'm going to round that to 72.2%. And I have a reason for doing this in a moment. So now I'm going to find the percentage of nitrogen. Percentage of nitrogen. So my part is going to be the mass of the nitrogen, 3.48 grams, over the total, 12.51 grams again, times 100. And if I do that calculation out, I get 27.8%. Now the reason that I went out 1 decimal place here and 1 decimal place here is because if I add these together, in a perfect world, I should get 100%, and that's a nice check to make sure that I've done all my math correctly. 2 different ways of doing percent composition problems. On the Regents exam, much more common to find an example like this where they give you a compound and they ask to find the percentage of one of the elements that are involved with the compound. Finally, let's talk about hydrates. And this is always a complicated problem with students. All a hydrate problem is just another percent composition problem. Part over the whole times 100, where the part typically is just your total mass of your water. What is a hydrate? A hydrate is defined as an ionic substance that includes defined amounts of water. So we're going to see water as part of the crystal structure. The water molecules are going to be shown as part of the formula. That's going to be key. Compounds that contain attached water molecules are called hydrates, and substances that have had their water molecules removed are called anhydrates. Really critical to know the difference between these two. Now, I know this is an issue with everyone. I fully acknowledge it, but you must deal. The dot, which many of you know as multiply in math, The dot in chemistry, especially found in a hydrate formula, means add. Adding, we're adding. So the gram formula mass of your anhydrate plus the total mass of your water. The dot in the formula does not mean multiply, but add. So if I look down here, I have copper 2 sulfate, dot, pentahydrate. That dot basically means we're going to take the gram formula mass of the copper 2 sulfate and add it to the total mass of the 5 water molecules. Don't be misled. This dot right here means add, not multiply. So let's look at 2 quick examples of hydrate problems. Quick note right here, we were just talking about copper 2 sulfate pentahydrate. This little image right here is copper 2 sulfate pentahydrate being hydrated. So this is with the water. If all the water is removed using typically a Bunsen burner or a hot plate, our copper 2 sulfate is going to turn into an anhydrate and the water has been removed. Let's look at our first example here. Find the percent by mass of water in magnesium sulfate heptahydrate. So the first thing that I'm going to do is find the gram formula mass of MgSO4, which I did earlier in the video. And if I look up the gram formula mass of MgSO4, it is 120 grams per mole. Then the other thing that I need to do is find the total mass of the 7 water molecules here. Water, H2O, has gram formula mass of 18 grams. And then I'm going to multiply that by the coefficient, which is 7. So 18 times 7 is 126 grams. And then if I add these two together, the 120 plus the 126, I get a total mass of 246 grams. So again, we're still dealing with part over the whole times 100, except the part here is the total mass of the water, and they'll be really specific about this. So I look at this and I say, well, the total mass of my water is 126, so 126 grams on top. The mass of the total is 246. That is going to go on the bottom times 100. The percent by mass of water for this particular hydrate is 51.2%. Now let's look at a little different one here. This is not common on the Regents, but could they ask you this? Yes, they could. Absolutely. It's a different type of example that we're going to look at. This example asks, find the percent by mass of the anhydrate in calcium chloride dihydrate. So here's my calcium chloride. This would be my anhydrate part. And then the dihydrate is the 2 water molecules coming together. First thing I need to do is find the gram formula mass of CaCl2. And if I do this really quick, it's around 111 grams per mole, depending on how you add up the chlorine atoms together. So I'm going to list it as 111 grams per mole. And then again, we know that water has a gram formula mass of 18 grams per mole. And we look at this coefficient right here, which is 2. So we're going to multiply that by 2, and we're going to get 36 grams. So if we add together the 111 and the 36, we add them, we get 147. So 147 grams. So again, we write our formula, part over the whole times 100. 100. Now this time, my part is the anhydrate. I'm not going to put the water on the top. Nope, I'm going to put the anhydrate. So this is 111 grams. That's going on the top because that's what I'm looking for. The total mass of the hydrate is 147 grams. And then again, I'm going to multiply this by 100. My percentage for this one is 75.5%. 2 different perspectives of how you can approach hydrate problems. So what did we learn in this review? Well, we did a very, very, very brief review of significant figures, always worth going over. We talked about how to find the mass of a compound. We looked at percent composition and again reference to table T because that's where the formula is located. And finally, we did some examples with hydrates. Need more help? Feel free to contact me. And of course, as usual, I'm always looking for feedback. Have a great day.